All right, so we are going to start right at lesson 29, which deals with rewriting your rates using different time intervals. And then we're going to move into Newton's law of cooling. And Newton's law of cooling, yes, is that scientist that you've learned about, I don't know, what, middle school? When was the last time you learned about Newton? Probably like 8th grade, like all the little physics things that you did. So I'm going to start right at the top here. You are going to need a calculator out for these. And everything today is going to involve really small little decimals, okay? So your first example here, we have the annual population of the blackbird, and you have this equation here. So 750 is the initial number of blackbirds that you started with. T is the number of years. So in terms of the monthly growth rate, the population can best be approximated by what? So what you're going to learn today is how to rewrite using equivalence models. So what I want to do is I want to take these answers and figure out which one gives me that equivalent expression. So obviously choice A is not equal to it. So this one's immediately out. Now, letter B, we've talked about this before, but just real briefly. You guys remember how we discussed pulling the 12 in to get T by itself? That is what you need to do for these today. So I rewrite it like this. I'm going to go 1.012 raised to the 12 to the T. And all I'm checking for in the calculator is this part. So this is going to get typed right into your calculator. And we are just looking to produce an equivalent function to the one above. Okay, so if you type this in, and again, with these questions too, I think I warned you about this in the past, they are often not perfect, okay? So what did we get from that decimal? Did you guys get like 1.15389? What do we think? Is that pretty close? It is. So this is where you have to kind of trust your gut instinct. If you want, you could do the rest of the answers, or you could assume that that's the answer and it's the closest. But just, I won't make you do them, but just to discuss. This one, I would pull in the 12 too, right? So I would just go 1.16 raised to the 12, which is obviously not going to be the answer. And then what would I pull in this one? What would I pull in to get T by itself? I see it. 1/12. Okay. So my closest answer, yes, would be choice B. Okay. So that's what you're going to work with today. You're going to rewrite using equivalent rates over varying time intervals. The most common time intervals that we see are monthly. And monthly is obviously going to use a 12. You can see daily. And we don't care about leap years, okay? So 365. Those are your two most frequently used time intervals, okay? So what we're going to be doing is we're going to write your formula. We're going to go 1 divided by the new period of time raised to the new period times T. Why? Because this produces an equivalent rate, because those would essentially think about canceling. So we're going to start right with number 1 here. So it says that $1,000 is invested in an account that earns 5% interest per year. When we earn, do we do 1 plus or 1 minus? Yep. Very good. So this is going to be 1 plus. 5% is going to be 0.05. And this is going to represent my principal investment. Okay. So it says write an equation to calculate the final amount of money over a given time period T. So I am going to go A of T, the equation, is equal to 1,000 And then I'm going to go 1 plus 0.05, which is 1.05. And then this is raised to the p. That's it. Now we're going to start manipulating this. So letter B says, write an equation to determine the monthly interest rate. Month means what number am I going to use? Yep. And I'm going to follow this formula right here. So I go A of T equals 1,000 parentheses 1.05. And the formula goes 1 divided by the new period of time. So I go 1 divided by 12. And then I raise this to the new period times t. Okay? Now the only part we type in the calculator is just the portion with parentheses around it. So I want you to make a note. This is the only portion that goes in the calculator. And you're going to get a decimal. All right? It's not going to be pleasant, but you need to round this. What did I do? 1, 2, 3. I want 5 decimals on this one. You'll see why. So we're going to go 1,000. And in the calculator, that should give me 1 point. Did you guys get 0.0013? So you're only typing in just the bracket. So 1.05 raised to the 1 divided by 12. Oh, yeah. Why did I say the wrong? Yeah, I'm looking at the wrong decimal. You're right. 1.00 was close, so just this was different. Go ahead, Josh, say it again.
1.004.
That's better, thank you. 0407. Thank you, they're all really teeny. And then raised to the 12t. Perfect, thank you for catching that. So now we need to figure out the actual rate. This part is up to you guys. You don't have to show this if you don't want. Is this growth or decay? Growth is bigger than 1. So what you're going to do is subtract 1 and move the decimal 2 places. So this is growth. So what we're going to be doing is subtract 1. So I'll show it on maybe like one of these. But again, this gets redundant. So if you don't want to show this every single time, you don't have to. So this would be equal to 0.00407. And I move my decimal 2 places. And yes, this is very small. So my rate is equivalent to 0.407%. Okay, how's that one? Okay. All right, so next, we are going to take this equation and we're going to determine a daily interest rate. So I want you to make a big note here because this gets confusing if you forget it. To write it as a daily rate, what I do is I use the original, not this one. So I'm going to use my original. And all I gotta do is type it in. All right, so I have A of T equal to 1,000, and then 1.05. And then what do you suppose I'm gonna use for daily now? Yep, so the formula says I do 1 divided by the new period, 365 days. But again, I have to produce an equivalent expression. So this always goes out here too. We just don't do anything with it. So to get my rate, I'm only looking inside. So this gets typed in the calculator. And I think this is the value I was looking at before from my calculator. All right, so I get A of T is equal to 1,000. And this was what, 1.00013. Yep, that's where I got that from. And then raised to the 365t. So again, for this next part, this is entirely up to you. Would you guys agree it's still growth? Would I do the same stuff as here? I would. So you can show it or not. It's up to you. I guess I'll do it maybe one more time. So in my mind, I'm thinking this is growth. So therefore, I take my decimal and subtract 1 from it. So minus the 1, I get 0.00013. And then again, I move my decimal 2 places. So very, very tiny. So this is R is equal to 0.013% growth. Okay. How's that one, okay? And if you watch a lot of TV and you see the commercials about the credit cards and the APR, this is what they do with your APR each month, okay, if you don't pay your bill. So number 2, this example, you saw a little glimpse of this maybe a week ago, and I told you we're going to do more with this, so it comes up right now. You have $250 invested into a savings account that earns. So earns means I do what? Yep, 1 plus growth, 0.15. And do you guys remember this? It doesn't occur every year, but it occurs every certain number of years. You remember that came up? We have to do something special with this. So this means my exponent is t, you remember? Excellent. Yep, just like that. Okay. So write an equation to calculate this. So I'm going to go A of t equals $250. And I'm going to go 1.15. But this occurs not every year. T divided by 3. So now what you're going to do next is you are going to find just the yearly rate. That means on the outside, I want t by itself. So what I do is I pull in the 1/3. So I go A of t is equal to, think about it like distributing it right in. So I go 1.15 raised to the 1/3 to the t. That's all you have to do for this part. Now you type that right in the calculator. And what do we get? And again, these are a lot of really small decimals. 1.04768. Thank you. Perfect. So again, you have another growth example, which makes sense. That's what your money is doing. So I take that value, I subtract 1, and I move my decimal 2 places. I bet you can do that in your head. What's my percent? Exactly. Yep, 4.769%. Nearest hundredth now, so we've got 4.77% growth. Awesome. So next, it says, what is the monthly interest rate? Now you want to be very careful. When you go to months now, you want to pull from the years. So for this one, I'm not going back to my original. I want to rewrite this in terms of just months. So I'm going to take this number and raise it to the 1/12 now. So I go A of t equals 250. And I'm going to go 1.04769 raised to the 1/12 to the 12t. And again, the only part that goes in the calculator is just this. And write it accordingly, however far you kind of feel like you have to take it. So this is equal to A of t equivalent to 250. And I'm going to go, did you guys get 1.00389? Perfect. Raised to the 12t. And then you finish. So what's my percent on this one? It's still growth. Yep, awesome. 0.389%. growth. Perfect. Again, that's a really small amount of interest to be earning on your money. Better than nothing, I suppose, though, right? You know, pennies add up over time. So very, very small. All right, next example. So the amount of caffeine in a patient's bloodstream decreases. What do we have to do different? Exactly. 1 minus. Awesome. By half. So what's that as a percentage? Yep. But it doesn't occur every hour. It occurs every 3.5 hours. So what does that mean for my exponent? Awesome. T divided by 3.5. Perfect. A latte is going to contain 150 milligrams of caffeine, which is absorbed into the bloodstream almost immediately. So assuming that the latte was the only source of caffeine, write an equation modeling the amount of caffeine in the bloodstream in milligrams at time t. So I'm going to say A of t equals. My initial value comes first. It's not money this time, but it works the same way. So 150, and then 1 minus 0.5 would just be, and then this is raised to the t divided by 3.5. Now you're going to take it further. So part B, what is the hourly rate of decrease? So I need just 1 hour, not 3.5. So what do I have to do? Yep, you guys are both right. I'm going to pull in my exponent is what you want to kind of think. So I have A of t equal to 150 times 0.5 raised to the 1 over 3.5 to the t. All right, and then that's just calculator work again. What do we get from that part? Trying to speed it up for you. 0.2034. Yes, thank you. And then this is A of t equals, because we want equations, 150 times that. Okay, so this one's a little bit different. This one's not growth anymore. Because when you drink caffeine, you definitely don't want it to keep increasing in your bloodstream. That would be bad. So I have to flip this around again. So instead of doing the value minus 1, I just do 1 minus this. So 1 minus 0.82034. Does anyone have this decimal? So like 8. Thank you. And then you're going to move this 2 places, and then you're good. But just if you're going to label this answer, this is decay and not growth. So this would be equivalent to 17.98% decay, because it is leaving your bloodstream. So now letter C. How much caffeine is present in the patient's bloodstream after 10 hours? So you have 2 equations here. Which one do you think is the most accurate to plug back into? The hour, yep, the one at the very, very top here, because this one you did rounding to. This one we did no rounding, so use your original because yes, you can. So use your original for the most accurate answer. Because again, you have that option here. So I'm going to go 150 times 0.5 raised to the 10 over 3.5. And what do we get from this one? How much caffeine this would be in milligrams? Yep, thank you. 20.702 milligrams. Perfect. Good. Any problems getting those? So number 4, another one to set up. You have a population now of 13,000 people, but this time it's growing. So growing means I'm back to what? Constant rate of 22% is 0.22. Every 5 years indicates my exponent is t divided by 5. Write an equation to represent this. Population, I'm just going to go P of t instead. You don't have to, it doesn't make a difference, but in case. So this is 13,000, and then this is 1.22 raised to the t divided by 5. So now we want, what is the percent per year? So once again, just practicing pulling that power in. So again, I'm going to make you a little note here to pull in the 1/5, so the exponent. I'm going to go P of t equal to, and 13,000 and 1.22 to the 1/5 to the t. And that's it. You're just rearranging your rate, essentially. So from this one, what do we get? Thank you. Appreciate your efficiency. So this is 13,000 here. So this is going to be another growth example too. So from this guy, I've got growth. I'm going to go -1, move my decimal 2 places, and what do we get for our percentage here? Very good. So 4.057%. And again, this one, if you wanted to label it, would be growth. All right, so letter C. What is the percent growth rate per month? Again, to do this, I can't use part A. I have to use part B. However, we are going to have a slight rounding error, but for our purpose, it's okay. So I am going to pull this equation down and go P of t equals. And I'm going to go 13,000. And I'm going to just use this big decimal, 1.04057 raised. What do I do for monthly? Yep. So 1 over the new period of time. And on the outside, to keep it equivalent, I go 12t. So calculation for the middle part. So I have a 13,000 on the left still, and that decimal. All right, really small little guy here. I got 1.00 and 332. Do you guys agree? Perfect. Raised to the 12t. So you're going to take that, subtract 1, move your decimal from this, and what do we get for our rate this time? What is this point? 332%. And that is equal to your R. We touching on how to manipulate those formulas? Because with that, the t over 5, and you have to create an equivalent rate. And right here, those 12s would cancel. So that would be your reasoning. Yep. If you needed to just sub something back in, then you could absolutely use the original there. But nope, if you're moving forward with it and breaking down your time period, you have to use that decimal. Good question. All right. So this one, I think we've kind of got the hang of that. So I'm going to skip. And I'm going to have you jump right on over to Newton's law of cooling. So this other problem, you're going to do that one tomorrow anyway. All right. So this is another nice application for you to show you how what you've been using with your logs and your e's can be applied to a real life situation. So this is Newton's law of cooling. This is, yes, a scientific application. So this is used to model the temperature of an object of some temperature placed in an environment of a different temperature. So we do heating and cooling with these. The temperature of the object T hours after being placed in a new environment is modeled by this formula. You don't have to memorize that formula, okay? Never. So T of T is the temperature of the object after T hours. T of A is the ambient temperature, what you're going to place the object into. And T of 0 is the initial temperature of the object, K is your decay point. So here's how this works. A pot of tea is heated to 90 degrees. So that represents the temperature of the object. And it's poured into a mug and taken outside. Okay, so time out, let's just talk about that. You have a hot cup of tea and you're gonna go outside. What's gonna happen to it? It's gonna cool down, yep. So outside the temperature is 18 degrees. What do you think 18 represents in the formula? Exactly, T of A. After 2 minutes, that's just T, the temperature of the cup of tea is approximately 65. So what's this one? T of T, yep. So that's your left side number. So it says find the decay constant to the nearest 10,000. So I'm going to do my formula. So my formula goes T of T is equal to temperature of the object plus, I'm trying to remember which one comes first here. I'm sorry, always mix those up. So we're going to go T of O minus T of A and E raised to the negative KT. All right, you're going to sub into this. So T of T, the temperature of the object after 2 minutes is 65 degrees. I'm going to say 65 is equal to ambient temperature of my environment was, I'm looking for it, 18, thank you. Plus temperature of the object initially was 90. And then minus the 18. And then E raised. We don't have the decay constant, that's K. But I think we have T. 2. Yep, thank you. All right, so you're going to solve this. But just like you've done in the past. The first step, subtract your 18 over. So I'm going to go minus 18 minus 18. What is this, 47? Equal to 90 minus 18 is 72. E raised to the negative 2K. That looks better. Why do you solve these for homework? What did I tell you to do with the 72? Whenever there's a number there. Yep, divide it out. Excellent. I'm actually going to just leave it like this. So I have 47 over 72 is equal to E raised to the negative 2K. All right. Tell me what you know about this now. How do we get rid of E? Natural log, very good. So on the left, I'm going to do the natural log of 47 over 72. And then on the other side, it cancels, and I just get negative 2K. So to finish, I'm going to divide by negative 2, divide by negative 2, and can someone get me this answer to the nearest 10,000? K equals, I don't remember what this works out to be.
0.2132.
0.21, 2 more places.
213, and then 3, and then a 2 round.
Thank you. Perfect, so that's your decay rate. So now letter B, write an equation for the temperature T as a function of time. So T of T with nothing known on the left now is equal to 18 plus 90 minus the 18, or you could simplify that, it doesn't matter. e raised to the negative 0.2133 t. So that would be your general equation, and you could sub anything into that that you needed to. So that follows with part C. To the nearest degree, what is the temperature of the tea after 10 minutes? So that's going right into that equation now. So I'm going to go T of 10 is equal to 18 plus. I'm going to simplify that now. 72 e raised to the negative 0.2133 times 10. If someone have this yet, you're just going to type it right in. Type it in.
We got 26.5306.07.
26.53. We'll take it. Oh, it just said nearest degree. So thank you. 27 degrees. Perfect. All right, and then B. Determine by what percent the temperature of the mug is decreasing each minute. So all we need to do, I'm going to grab it from right up here, is I just need to type now this in the calculator. Just like we were doing on all those other problems. E raised to the negative 0.2133. And I'm going to get a value for this as well. So E raised to the negative 0.2133. Did we get like 0.8079? So again, this is decay. So I'm going to go 1 minus this and move my decimal. So 1 minus, and then move your decimal over. And then we'll do one more quick one like this. All right, I'm getting like 19.2%. And then you're good to go. So 19.2%. How's the first one with the cooling? Okay. So your last part today also works in reverse. So we're also going to do something that heats up. So I gave you on the back 2 different thermometers. They're sitting in a room that is 22 degrees Celsius. So that is your T of A. Just like the other one that we went outside. 2 different ovens. Okay. So again, this is going to be heating up because obviously an oven gets hot. So this says, does the table and the graph for each thermostat support the statement that Newton's law of cooling also applies when the surrounding temperature is warmer? Yes, because what's this doing? Heating up, so yes. I'm going to say it also works in reverse. You guys know this. Part B, nice and quick. Which thermometer was placed into a hotter oven? What do we have? 176 versus, what is this? Someone ballpark it. Is it 230?
Yeah.
Thank you. Hard to read there. So 230 degrees. So which thermometer was placed into a hotter oven? That must be thermometer 2. I'm gonna go thermometer number 2. Reasoning, 230 degrees versus 176 degrees. Okay, so using a generic constant, write your formula. So formula goes, and do this too, because this was like a repeat. So you can use this space here for the other guy as well. So I'm gonna go T of T equal to. So I am going to begin here with my ambient temperature here, which in this case is going to be your oven. So for the first thermometer, the oven was 176 degrees. And then I'm going to go plus. And I'm going to go my temperatures here. So I started at 22. And then I'm gonna go minus the 176 raised to the E times, we don't know it. So using a generic time value, did we know T though? I think we did. How long did it take to get to 176? 14, yep. So I'm gonna do negative 14 and then K. Formula for thermometer 2 is gonna read T of T, but this one, I think it hit a higher temperature. So all you're gonna change is this is gonna be a 230, and then I'm gonna go plus 22, and then minus the 230, and then I'm gonna go E raised up to the, was it 14 as well? 10, thank you. Negative 10. All right. I think there was, nope, I didn't need you to do that part. Okay. How do your graphs differ when your object is warmer? All you're going to see instead of exponential decay is what? Exponential growth. So this is more of a situation that resembles exponential growth instead. Obviously, it's not going to continue to heat up forever. It will plateau, but it's just going to go the opposite direction. Okay, with Newton's law of cooling, we're going to stop there for today. How do you guys feel on those? It's just nice to show you applications. So tomorrow we're going to finish just a bunch more applications with these. We'll do some more financial ones. We'll do your mortgage formula tomorrow as well. Assignments for this week, just in case you want a heads up now. Let me bump to my other screen here. Oh, come on. So for this week, you are going to have some problem sets to complete, and then there's 2 assignments that will be on Delta Math, okay? No quiz this week either. So just those 3 assignments will be, you know, the Delta ones are due by Friday. The Monday one, I'll kind of check when you guys return because you're not here Wednesday this week. Okay? Questions on anything? All right, you got like 5 or so minutes if you want to get working, or you can take a break too.